So I've just done a couple of titrations with 0.1 mole per decimeter cubed hydrochloric acid and 0.1 mole per decimeter cubed sodium hydroxide. And I've used two different indicators and I've got the same end point as you would probably expect. So what I'm going to do now is I'm going to change the acid to 0.1 mole per decimeter cubed ethanoic acid. I'm going to do exactly the same thing and see if we get the same answers. So the first titration I'm going to do is using the methyl orange indicator, and you can see without any sodium hydroxide in, the colour of methyl orange in the ethanoic acid is this sort of reddy orange colour. So I've got my colour change. You can see there we've gone from that sort of reddy orange colour to a definite orange colour. So the reaction, according to the indicator, looks like it's over. And if I just show you the burette, you'll be able to see the value that I've got on the burette. And there's the meniscus sitting on the 4.8 line. So we would record that as 4.80. So quite a low end point. So I'm all set to go with our second titration now. We've got phenolphthalein indicator in there with our ethanoic acid, and this indicator remains colourless in acid, and when a sufficient amount of alkali has been added, it will go pink. I'm at the 5 cubic centimetre mark for the addition of sodium hydroxide, and you can see very clearly that that has not changed colour. And if you just look at the flask in the background there, this is the one that had the methyl orange in, 4.8 cubic centimetres, and this changed colour. So something strange going on. We've finally got our colour change, so I'll just show you where the burette's at now. So there's the meniscus and it's sitting on the 24.9 line, so we'd write that as 24.90. Very, very different to the first titration. So there's the board with my two results on. You see I've written the equation up across the top there. So ethanoic acid and sodium hydroxide would give sodium ethanoate and water. And I used 0.1 mole per decimeter cubed acid and 0.1 mole per decimeter cubed alkali. 25 cm cubed of the acid had been pipetted into the flask, and so because of the 1:1 mole ratio and the fact that these are the same concentration, you would expect that we would need 25 cm cubed of sodium hydroxide as well. So it's pretty obvious that this result here is the right result, but this one here is way off, isn't it? So let's have a look at the reason for that now. To explain what's going on here, I've got the titration curve, typical titration curve for a weak acid with a strong base. So weak acid starts at a pH of around about 3. We'll get this flick up, and then it sort of, the pH rises gradually until we get this sharp rise in pH. That's obviously the end of the titration. Equivalence is the centre of that vertical section. Strong base, so then it sort of tracks along the line of about pH 12. Now you may not have noticed, but on the labels for the indicator bottles we've got this information here, pH range, just turn that round, pH range 2.9 to 4.6. and phenolphthalein pH range 8.3 to 10. So indicators work over a sort of small pH range, and if we look at where this pH range sits on the titration curve, 2.9 to 4.6 is down there. So this indicator is changing colour right down here, where the pH changes between that range there. And so that's where we're at in the titration, where the indicator changes colour. Well, you can see that's nowhere near the equivalence point, and so that's why we got this ridiculously low end point, or so we thought, of 4.8. If we look at the phenolphthalein bottle now, so this changes over the range of 8.3 to 10, which is about somewhere there on the scale. You can see that this is changing colour at the right pH for our titration, because we want the indicator to change colour where this vertical section is. So phenolphthalein sits right in there. So when you're choosing an indicator for a titration, you need to be aware of its pH range, and it must fall within the vertical section. If it doesn't, you're going to get a false reading like we did there. At the very beginning of the video I mentioned that I'd done 2 titrations with the 0.1 mole per decimeter cubed hydrochloric acid and the 0.1 mole per decimeter cubed sodium hydroxide, and I got the same end point for my titration with both of the indicators. And I've scribbled, it's a bit messy, sorry about that, but I've put on the titration curve for strong acid, strong base, which is the red curve. And hopefully you can appreciate now why either of those indicators are absolutely fine for this titration. So the range, the pH range for methyl orange, 2.9 to 4.6, well that's there on my pH axis. So it's going to catch that magic drop, it's going to change colour when that magic drop goes in for equivalence, and we get the vertical section on the curve. Phenolphthalein is also on the vertical section, and so it's absolutely fine. Either indicator is absolutely fine.